The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna, for introducing the session. A very good day to everyone, and thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jiaying Meng from ITU, the International Telecommunication Union. Today, we are excited to host another interesting talk titled Radio Resource Management for 6G NX Subnetworks. This webinar aims to explain the complex environment of NX subnetworks, the stringent low latency requirements, and call for the adoption of advanced artificial intelligence solutions. The general objective of the challenge is to develop AI or machine learning-based centralized or distributed techniques for joint subband and power allocation in hyperdense deployments for industrial subnetworks. As always, we're counting on you to help create an engaging discussion. If you have any questions, please type them on the video wall and we will take them during the Q&A session right after the talk. Before officially starting the session, I want to introduce our esteemed speaker, Saeed Hakimi, who has rich experience in wireless communications. Saeed Hakimi is a postdoctoral research fellow at Aalborg University in the Wireless Communication Network section of the Department of Electronic Systems. His research primarily focuses on wireless communications, signal processing, and machine learning. And as always, my colleague Vishnu, who will be taking charge of the Q&A session. Without further ado, I would like to pass the baton to Saeed. Saeed, the floor is yours.
Hi, everyone. Thank you, Jiang, and all of the ITU teams. Today, we are kicking off the AI/ML challenge on radio resource management for 6G NX subnetwork. But before diving deep into the topic, let me share my screen. I hope all of you can see my screen now. Yes, let me briefly introduce our section. Aalborg University is one of the main universities in Denmark. It has 3 campuses, more than 20K students, close to 4K employees, and 5 faculties, which IT and design is one of them, and Department of Electronic Systems within the Faculty of IT and Design, organized in 6 sections: AI and Sound, Automation and Control, Communication, Media and Information Technologies, Antennas, Propagation and Millimeter Wave Systems, Connectivity, and our section, wireless communication networks. In our section, we have 30 researchers, 3 full professors, 5 associate professors, 7 postdocs, 2 researchers, research assistants, and actually 12 PhD students. Of course, our section is participating in lots of projects. Among them, the European projects, actually 2 of them are more related to our discussion today, which both of them are SNS projects. The first one, 60 Shine, focuses on key technology components for Unix subnetworks. And the CENTRIC, which is again SNS project, leverages AI techniques to a top-down modular approach to wireless connectivity. Well, as part of the convergence of 60 Shine and CENTRIC, we consider AI/ML approaches to address some challenges of 6G Unix subnetworks. So as a joint activity, we are proposing this AI/ML challenge today. Yes, as an introduction, I should say 6G Unix subnetworks are short-range, low-power cells for entities like robots, vehicles, production modules, classrooms, and like that. These subnetworks offer highly localized wireless coverage for various use cases. They support diverse services with extreme requirements in reliability and service availability, which of course may surpass 5G capabilities. Unix subnetworks can be part of a parent network, let's say 6G infrastructure, and they may offload the most demanding services to the broader network. There are plenty of use cases for the Unix subnetworks. Actually, we summarize them to 3 main categories. The first one is a consumer use case category. And in this use case, there are lots of use cases examples. The first one I want to mention is immersive education, which aims at enhancing the interaction experience of a group of students and teachers for knowledge exchange using media content and related technologies. Actually, it allows, of course, to enhance the students' experiences beyond an ordinary classroom. Of course, this concept can be extended to other fields like historic sites or museums and like that. The other approach is indoor interactive gaming. The other use case is indoor interactive gaming, which is about XR interactive gaming in an indoor environment, where 1 or more players play in a controlled environment. The next use case could be virtual live production, which is about virtual content production of live music. As you see, let's see, pointer, yeah. The illustration shows 2 performers, and each performer is in a different live studio. So we have more than 1 subnetworks in this use case. So in the live studios, cameras and microphones, the sensors are installed and connected, of course, wirelessly during the subnetwork. The next category of use cases is in vehicle. Due to the critical timing, reliability, and safety requirements of automotive functions and services, in vehicle communications nowadays, at least mostly rely on cable links. Yeah, there are lots of advances in wireless technologies, such as 5G or beyond 5G, developed by 3GPP, or Wi-Fi 6, developed by IEEE standardization. But it still remains a significant challenge to deliver wire equivalent bandwidths and reliable wireless communications that to be used in time safety critical systems like those implemented inside vehicles. We can see in the figures here that the sensors and actuators that are wirelessly connected to the, let's say, zone ECU are equipped with a 6G wireless communication interface, which their goal is to replace the wired communication interface. Of course, the wired communication interface for those devices which are not part of the 6G wireless subnetwork should be maintained. Yes. Of course, the scenario like the previous one, which we have more than one subnetwork, would be more challenging when multiple vehicles come into proximity with each other. Let's say, such as on a busy road, then it would be more challenging. Interference among the wireless subnetworks across these vehicles can potentially degrade the performance of the communication systems within each vehicle. Yes, the last use case category is industrial category. And the first one in this category is robot control, let's say wireless control of robot operation, which are usually relying on, again, wired industrial technologies. They support by very short communication cycles, let's say down to 50 milliseconds or even below. Again, this use case aims at translating such wired communication technologies over wireless. I can mention to the unit test cell, which is to perform quality assurance tasks of product parts in the manufacturing process, or a visual inspection cell, which performs quality assurance in the manufacturing process using, of course, video feeds. Again, in many manufacturing process, tasks can be distributed among a swarm of smaller or specialized robots. Then again, we have, let's say, more than one subnetworks. So in these scenarios, we would have a more challenging task. But let's discuss why radio resource management for Unix subnetworks is a challenge. Actually, we saw in different use cases that subnetworks by nature lead to highly dense deployments, which may contain uncontrolled and mobile subnetworks. On the other hand, they need strict latency and reliability requirements. So if a spectrum sharing, interference management, and in general, resource allocation not properly managed, they could lead to a degradation in the system's performance. But in which domain should be focused? Actually, in the time domain, interference coordination schemes may be unsuitable for actually low latency services, because it would be challenging to use this domain for low latency services. And on the other hand, at least for the low frequency use cases, the limited antenna of the, let's say, access points and devices make a challenge for spatial coordination. So it seems that dividing the spectrum into subbands and doing the subband allocation with, let's say, power control can minimize the mutual interference. So one may think that, yeah, we have 5G that introduced the concept of URLLC. So why do we need any further thing to the challenge? But at least we think that still the targeted 5G requirements may not be sufficient for the support of very critical services. So we need to rethink about the problem. Actually, there are different strategies for the radio resource management. If we suppose that there is a centralized controller in the subnetworks, and all of the subnetworks can connect to this centralized node, then we can use centralized approach. Of course, it has its advantages like more computational capacity, which lead to the global optimization, or let's say more efficient spectrum utilization. But on the other hand, disadvantages could be poor scalability, or let's say these approaches requires a communication link between all of the subnetworks and the centralized controller. And also, this approach is just applicable mainly to the licensed spectrum, not the unlicensed spectrums. But beside these disadvantages, some of the let's say services or use cases don't have any option except distributed approaches. Let's say, for example, mobile and life critical use cases like in vehicle and in body subnetworks, they need to use a distributed approach. Such use cases cannot actually entirely depend on an external network because intermittent communication links can be experienced due to the coverage holes. So, for example, let's suppose vehicles driving in a tunnel or humans entering radio isolated buildings. So in these cases, for these subnetworks, decisions should be based on local sensing without explicit signaling. It means that they autonomously should decide about the radio resource management. Well, as a solution space, we have two groups of solutions. The first one, heuristic methods. Of course, something like the traditional optimization methods and heuristics, which have proven effective in certain contexts. For example, one well-known approach for subband allocation is representing the wireless network as a conflict graph, where cells are nodes and edges represents interference among the nodes. And then a graph coloring algorithm can be used for subband allocation. For example, coloring of a graph using a greedy algorithm. The other approach, which is at least newer compared to the CGC, is sequential iterative subband allocation, which is a centralized iterative algorithm to minimize the sum of weighted interference for subband allocation. Of course, for the power control, we can use any classical iterative methods, but we should note that if we write the problem, it would be, let's say, mixed integer linear program, which is of course non-convex. So it would have lots of challenges. But beside the challenges like, I don't know, complexity and execution time of the heuristics, and of course, iterative algorithms, the dynamic and complex nature of unique subnetworks demands a more adaptive and data-driven approach. So our hypothesis is that AI/ML approaches improve resource efficiency compared to the conventional methods. One of the main, let's say, goals of this challenge is to verify this hypothesis. But I should mention that there is no limitation on applying the AI/ML approaches. It could be any types of deep neural networks, I don't know, graph neural networks, or any types of reinforcement learning. Yes, but what is the challenge exactly? The target scenario is high dense subnetworks and high mutual interferences. And our use case is in factory subnetworks. So we suppose that there is a centralized radio manager that subnetworks can communicate to it and transmit local information, let's say local measurements, something like CSI via a backhaul link. So the centralized radio resource manager suggests the action. What is the action? Is the subband allocation and the power control. according to a global or local policy. The strategy could be centralized, distributed, or hybrid. For the solutions. But for the simplicity, we don't restrict the possible solutions. And on the other hand, the subnetworks, as I mentioned, could be mobile, but we just for the simplicity, we limit the challenge to static scenarios. Actually, as an input, we just have the snapshots of the channel realizations. So the goal is to develop AI/ML-based centralized or distributed techniques for joint subband and power allocation in hyperdense deployments for industrial subnetworks. So what we consider as an input to the model is simulated actually channel for in-factory scenarios. In the other hand, in the other word, we have multiple snapshots of CSI matrix. And the wireless channel model that we consider is based on the model that 3GPP released for in-factory scenario. And the channel gains has three terms. The first one is small scale fading based on Rayleigh distribution. Specifically, we are using Jake's model. For the pass loss, the pass loss model is based on the dense clutter and low base station height factory scenario from the 3GPP model. And for the shadowing, we are considering a model that is actually correlated shadowing. Yes. So what is the data set? As I mentioned, the data set is based on the simulated factory environment. And the focus here is on uplink transmission. Each subnetworks, we suppose that serves a single device and not more for the simplicity again. And of course, they utilize the entire available bandwidths for the transmission. In each in-factory subnetworks, the access point is positioned at the center of a circular coverage area with a radius r, and the device is located at a distance t with a minimum proximity of d min to the access points. We consider the number of subbands are 4 for wireless communications, and the power level could be continuous value. There is no limitation in the continuous value. Of course, we have a maximum transmit power limitation. So if I want to mention the parameters, the factory area is 20 by 20. The number of subnetworks is 20. The number of subbands is 4. Subnetwork radius is 1 meter. Number of devices per subnetworks, as I mentioned, is 1. The minimum distance between access points are 2 meters. Actually, the device to access points minimum distance is 0.8, and the shadowing standard deviation is 7.2 dB. And the clutter density and clutter size is 0.6 and 2, respectively. The decorrelation distance in the correlation shadowing model is 5 meters. The maximum transmit power is 0 dBm. The bandwidth is 40 megahertz. The center frequency is 6 gigahertz, and the noise figure of the receiver is 5 dB. Actually, we generated 200,000 of snapshots of subnetworks deployment. And of course, we also save the location of subnetworks and the CSI matrix. If some of the participants need more snapshots, of course, you can use the Python scripts to generate additional data. I think the materials are online and it's publicly available. Okay. As I mentioned, we have 2 files. The format is, of course, NumPy. I think it should be easy to load the data. And about the dimension of the inputs, the CSI matrix is k by n by n, which k is the number of subbands, n is the number of subnetworks. So it means that each of the subnetworks can have some interference to the others. And we also have the location of each subnetworks, which we save the coordination. I mean, so the dimension would be n by 2. As I mentioned, for simplicity, we just consider static scenario. Of course, subnetworks can be mobile, but to reduce the complexity, we just focus on the static scenario. On the other hand, someone may consider just location of the subnetworks as the input to the model instead of the CSI matrix. Of course, it would reduce the performance, but it makes the model simpler and less complex. So maybe consider these input beside the CSI for those scenarios that I mentioned for more realistic scenarios. But we don't restrict the solutions to be, I mean, just use one of the inputs. You can use both of them. Of course, as you see, the goal is not considering all the practical aspects of Unix subnetworks and let's say try to solve all the issues to this challenge. The target is to try find some AI/ML approaches that improve resource efficiency, of course, compared to the conventional methods and as much as possible. So for the evaluation metric, we consider the rate at the median. So this metric show the average performance that the user with experience. On the other hand, we consider the rate or equivalently the spectral efficiency on low percentiles. I mean the 10 to the minus 3. So this metric can show us the system performance under extreme conditions for critical, let's say, use cases. So the final performance score would be weighted some of the normalized rates at median and at low percentile. And yes, the weights are 1/3 and 2/3, which means that we have more weights for the low percentiles. Yes, of course, if the performance of the solutions is close to each other, we consider the complexity of the solutions as a factor for the evaluation of the solutions. Yes, for the submission, of course, a test data set will be provided to the competitors before the end of the competition. And our participants should use their AI/ML algorithms to evaluate the performance of their algorithm on the test data set, and they should provide 3 files: a CSV file, which contains 2 columns. The first one, subband index, and the second one, power level. We also need a file that contains all of the materials, contains a README file that explains how we should run the code. And if there is any pre-trained model, we need it. And actually, it should be contain any necessary material that we need to replicate the solutions. Besides that, we need also a PDF document which explain the methodology and some explanation that we need to replicate the solutions. Of course, whenever you have any questions or comments, you can send me an email. Yes, of course, there are lots of references if you search, but I just mentioned to some of them here. The first one, you can find some vision and some challenges of the unique subnetworks. I just mentioned to one of them, actually one of the most important challenges of the unique subnetworks, which is our target challenge in this discussion. As I mentioned, this work is part of the 2 SNS projects. So for more details about the use cases, service requirements, and these things, you can refer to the deliverable 2.2 of the 60 Shine project. Of course, there are lots of heuristic approaches on the papers and some AI/ML approaches that you can refer to them, at least for get some view about the problem. Yes, I think that's all I wanted to share with you about the challenge today. I hope the challenge was interesting enough to attract multiple participants. Yes, and at the end, I should say thank you to the participant and ITU team, of course, for facilitating the challenge. Yes, thanks. If there are any questions, I'm waiting.
Thank you very much, Syed. I think that's a very clear problem statement. If the audience have any questions, potential participants who have questions, please put in the Q&A, and we will take it up. Meanwhile, Syed, let me ask you my set of questions. The bitrate that you mentioned, right? How do you measure it? And can you explain, like, for each of the scenarios, how do you measure the bitrate in the challenge with respect to the challenge, please?
Yes, actually, we can calculate the spectral efficiency or equivalently the rates. I think we are making the life easy. So we use the famous formula from the Shannon. So we can calculate the spectral efficiency for all of the scenarios the same and using the Shannon formula. So it's not that much complicated. Actually,
so that is part of your reference code, is it?
Yes, the goal here is not, as I mentioned, to consider all of the challenges of the unique subnetworks usages in practice. We just focus on the main challenge, which is a high density of the subnetworks.
Great. Okay. And in your input, you don't have the bitrate at all, right? So in your reference code, you would calculate it, as well as the participant would use the same code. Is that how it works?
Yes, actually, our metrics for evaluation of the different solution is the rates, as I mentioned, based on the Shannon formula, in the median of the CDF and in the, let's say, 10 to the minus 3, the point 10 to the minus 3 of the CDF. and the weighted sum of these two metrics. So actually, the goal is to consider both the average performance and also the performance for the, let's say, URLLC use cases.
So for a participant who is not familiar with the formula, your code would automatically do it. They don't have to do anything. I'm guessing that's the case.
Yes, they don't need to do anything. Of course, if they want to have a vision about their solution, they can calculate these two metrics and see. I think there are some, let's say, benchmarks based on heuristics. That's I mentioned to some of them. And they can, I think, find them on the internet, at least easily, and compare their performance to the benchmarks and have a such, let's say, estimation about their solution performance.
Yeah, I think that's a great answer as well. I was about to ask that if there are some benchmarks and baselines which are
I think
there
are
already available.
But yes, if they couldn't find it, they can send me an email and I can provide some benchmarks for them. Of course, it's not some parts of the evaluation procedure, but at least they can have some estimation about their solutions performance.
Sure. Actually, for your research, do you have some reference to your papers? Do you have published papers in this space at all?
Yes, actually, I myself started.
Would you refer to?
Yeah, I think some papers that I listed in the reference, I think most of them was my colleagues' works. So I myself recently published a conference paper on EU CNC. I think it should be available online now. Of course, it's not indexed in the IEEE yet, but it will be. Yeah, I think that's the only paper that's available from my side. But there are lots of papers from my colleagues, Gilberto Parandinelli and Ramoniat Egon and the others. If they search, they can find lots of papers that will give some good inputs to the participants.
Great. Regarding the timelines, so can you I know we discussed, maybe you can summarize the timelines, please.
Yes, I think the challenge is open, as we discussed, to the all registration, and registration can be done until the 6th of September of 2024, and the submission deadline is 13th of September. So we expect that we can evaluate and finalize the solutions till the 30th of September. Of course, it's the rough timeline, but it should be something like that.
Regarding publication, so are you planning to? One of the things that participants ask us is also about publication opportunities, because there are different researchers who would like to publish their papers based on their work. So do you think it is possible to publish papers based on this competition?
Definitely, I think there is a very good opportunity for the publications. Actually, the challenge that I described was the initial step towards the RRM for the 6G Unix subnetworks. There are lots of more opportunities and more rooms to enhance the RLM. For example, in this challenge, we just discussed about the interference among the subnetworks, but there could be some external interferences. Let's say from other radio technologies which are active in the same location, or potentially malicious interference, something like jammers. So I think it could be one of the interesting aspects that they should, I mean, if someone want to work in this field, could consider. Or for example, when we say distributed approaches, we need some sorts of communication between the subnetworks. Probably, if we look at the 3GPP standardization, we can find something like side link or these things. But is it enough, or we need to add some more features to the side links? And I think it could be another field to do more research. Beside that, I think so far we just discussed on the communication, let's say wireless communication performance metrics, and we considered, let's say, CSI channel and these things as an input. Someone may consider the optimizing the application itself instead of just considering the communication, wireless communication metrics. As an input, someone may consider contextual data utilization, such as, I don't know, velocity, position, or these things instead of the CSI measurements. Or as a KPI instead of spectral efficiency, someone may consider the application itself as a criteria for the optimizing the network. For example, let's say AGV emission time could be, for example, one criteria. Yeah, I think there are plenty of opportunities to work in this topic. So if there are any volunteer, yeah, I think at least our section is open to collaborate.
Yeah, actually, those are that's a very comprehensive answer, by the way. I think the different variations of the scenarios that you have, they are quite exciting by itself. The uplink and downlink traffic patterns, I want to ask you about that. You have chosen to focus on uplink. I saw in the slides that you are focusing on uplink. Why did you take that decision? Is it a simplifying decision or a complicating decision?
No, it's not about the complicating. What we are doing here is just simplifying everything. So I think we just focused on the uplink, and as I mentioned, we just consider that each subnetwork is serving just one device. So it could be more complicated. Yeah, I think another challenge would be serving more devices within each subnetwork as a research topic. Yeah. Yes, there is no reason for making the problem more complicated at this step.
I think another thing which you have taken assumption is static. I mean, you're not considering any particular mobility pattern or anything like that.
Yes.
So I think that's another simplifying decision which helps participants.
Yes, as you mentioned, the mobility itself could be another opportunity to work on this topic. So yeah. I think here in our section, we decide to consider mobile subnetworks. I think it would be nice if some of the participants, if they are interested, consider the mobile subnetworks. We can provide the input. I mean the CSI in mobile subnetworks, which of course could be totally random movements, or it could be based on some predefined waypoints, which is more practical or near to more practical scenario. So I think, yes, there are much more room for work on the topic.
So coming back to the particular challenge as such, the compute capability required. I am guessing that the compute capability is not too much. I think a regular researcher from or a student from a university should be able to afford the compute capability that is required to model this problem. Can you confirm, according to your experiments, is that true, or
Yeah,
do you need GPUs? The basic question is, do you need GPUs?
Of course, as always, if you have access to the GPU, then life is easier. But if not, I think in the deployments that we are considering, we just consider 20 subnetworks and 4 subbands. So it's not that much that you cannot implement your model in the CPU. So it should be feasible. Of course, if there is any availability of the GPU, better. But I think CPU should work here.
Sure. So I have to mention at this point that ITU provides free GPUs. So it's like free lunch. Yeah. So we do provide. If some of the participants who are listening who would like to avail of our offer, please contact us, and ITU will make sure that you have GPUs. And then I want to ask about in general about data-driven approaches. So you did mention about data-driven approaches. I just to go back to your technology slides, you did mention. So there, and you just now mentioned deployment scenarios as well. I think one of the problems which we have seen in such cases is the complexity of both implementation and in real world deployment. So I want to ask your comments on when you implement these models, when you implement these solutions in such networks, especially for data-driven solutions, modeled solutions. So do you see implementation complexity as a limiting factor, as well as deployment capability as a limiting factor for such approaches as it stands? I mean, as of now.
About the computational capacity, I think if at least for the centralized approaches, everything is doing in the centralized controller. And for the scenarios that we have too many subnetworks, then it may be a challenge in the centralized node. Then we should take care about this one. Beside the computational complexity, I mean the implementation, we have then the challenge of signaling overhead, which would be really a challenge if the number of subnetworks is, let's say, huge. Then the signaling overhead would be too much, and the computational capacity that we need in the centralized controller would be huge. So in those scenarios, maybe we need to do some sorts of hybrid approaches, or at least we need to do some sorts of segmentation of the subnetworks and have some clusters to do these tasks in different clusters. But I think if the scenario is the distributed one, then the complexity of the implementation shouldn't be a limitation. Of course, it depends on the capacity of the computational aspects of the subnetworks, I mean the access points. But I think it should be manageable.
Yeah, I think your hybrid approach that you mentioned is quite interesting. I think that's probably more interesting to our industry partners.
Yes.
So yeah, maybe coming back to the challenge, I want to ask about data availability. When do you think the data is available so that the participant can download and experiment with it?
Yes, I think right now it's available. It's, if I remember, it's on the Zenodo website. If it's fine from ITU side, it's available right now. If it's not enough, we can upload it somewhere else. And yes, the participants can use this data set as an input to their models. But for the evaluation, and we will provide test data sets for all of the participants.
How
which
big is
of
the
course,
data?
I think which is similar to the data set that is uploaded. The number of snapshots, as I mentioned, is 200,000. So I think the size of the file wasn't that much big. I don't recall, to be honest, because I uploaded a few months ago.
Okay. Maybe we can discuss prices. We are kind of reaching the time limit, so prices. So ITU will definitely have some prizes, certificates we always give out. But from the university, do we have some incentives like internships or industry partnerships, or you already mentioned publication opportunities. So
Yes.
what are the incentives for the participants, please?
Of course, the opportunity for the publications, if it's open access, there should be some opportunities that university can support. About the other prizes, I think I should discuss with the managers, but I don't know, maybe we can discuss offline and probably let you know that if there is any opportunity to have more prizes from outside Harvard University, then we can inform you.
Thank you very much. That's all the questions from our side. I think this is a very exciting challenge. Thank you, Syed,
I hope so.
for patiently answering all our questions.
Thanks.
Back to you, Jain.
Thank you very much, Vishnu, for the Q&A session. And at this point, I would like to thank everyone for sparing your valuable time to join the session today. I would also like to express my gratitude to our speaker, Saeed, for his contributions. We have more sessions in the future. Please check the AI for Good program page for details. Please note that the challenge is open for registration and participation. The link for registration is posted on the video wall. You can start working your solutions and submit the results on the portal. Several prizes, including the certificates from ITU side, are planned to be handed out to winners of the challenge. Details are on the challenge webpage. And as my colleague Vishnu has mentioned, we are offering computes with GPUs that will be provided to challenge participants based on need. You can also interact with us and other participants on the Challenge Slack channel. We look forward to your future participation. Thank you for joining and have a nice day.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.